The getRandomElements method returns a type t, the same type marker that was defined in the class declaration. We can now use the random selection class that we have just defined by constructing a typed instance. The assignment to an integer variable choice is safe. We will always get an integer from the getRandomElement method of selector. This is true only because we constructed our selector instance using an integer for the generic type. The definitions for the add and getRandomElement methods have the same type as the constructor's definition, and the compiler will enforce this constraint. Let's try using the random selection class with a different type in the constructor, this time using the fruit enum class that we defined earlier. Notice that we were able to directly use the fruit return value from the getRandomElements method, just as we had done earlier with the integer. This is because we constructed random selection using the fruit type. You can define your own generics in cases where you want a class to work with objects of some type that you don't know until you construct the class, and where you want the compiler to strictly enforce the type restriction. The main advantages in doing this are safety and convenience. See the generic tutorial at this address, and the Java 5 documentation for more information on generics. Arguments and more arguments. Writing vararg methods. Java programmers often need to write methods that accept a parameter containing multiple values. This might take the form of a list or an array, for example. The same code could also have been written as several overloaded methods, each with a signature that takes a different number of int parameters. This sometimes makes the method easier to use, since the calling code does not need to create an array first. This is easier for the calling code if there are only a few values, since now we can use at 12, 14, 16 instead of add new int 12, 14, 16. However, there are problems with writing methods like this. Of course, we would need to write different versions of the method for each possible combination of parameters. But what we wanted to allow the most flexibility in how what if we wanted to allow the most flexibility in how the method is used without making a huge class with thousands of methods? There is a rather small limit to the number of parameters that this overloaded method will accept. In Java 5 you can write a method so that it allows a variable number of parameters and let the compiler do the work of packaging the list into an array. We are still dealing with an array internally, but the details are now hidden by the compiler. The following code rewrites the add method using variable arguments var args. Yes, those strange dots are real syntax for var args. Since this change requires Java 5, we might as well use the Java 5 enhanced for loop syntax too. Once you write the method this way, you can call it with as many parameters as you want. You can also pass an array, but not a list or collection object as the parameter. It's worth noting that you can use this shortcut only once when defining a parameter list, and it has to be the last item. The following would not work because the variable parameter is not the last item. Instead, you must write it as this. In some cases, using var args in a method definition can make the method much more usable. This is especially true in cases where a parameter list contains literal hard-coded values, such as int values shown in the example above. Being assertive using Java assertions. The parameter is always right. The programmer is always right. It's the compiler and interpreter that get it wrong. I'm sure you can identify with that thought process. As a programmers, we often make assumptions about the values of variables and write code that relies on these assumptions. As much as we hate to admit that we might be wrong in our design or implementation, variables and parameters sometimes don't have the values that we expect. Code will work properly only as long as the original assumptions that we made when designing and writing it still holds true. If the assumptions are not explicitly stated somewhere, then anyone reading the code, including you, will not know what they are. Future changes may violate those assumptions and introduce bugs that are difficult to locate. Many people document their assumptions in comments, so that anyone modifying the code later will avoid making such changes. Using comments to document assumption is a good start, but when something violates an assumption, the program keeps on running as if nothing is wrong. In some cases, the result is immediately obvious and the developer can fix the problem. Other times, there is a silent bug that might have a negative impact in another part of the application, or with distributed systems in another application altogether. Tracing such problems is extremely difficult. In Java 1.4, added the assumption feature to the language to simplify testing and debugging, strengthen documentation, and improve the maintainability of Java-based systems. You make an assertion by using a Boolean expression to test something that you are assuming about the current state of the system. If the assertion fails, the runtime will throw an assertion error. Here is a very simple assertion. We can say with some certainty that after we assign the value brain to the name variable, in its value will be non-null. If this is not true, then something is seriously wrong. This assertion is a statement of an assumption that we are making about the value of the variable at that point in the program. It would be silly and wasteful to do this for such a trivial case. However, consider the situation where multiple methods are affecting the same state of an object. We would like to be able to assume that the object is still usable afterwards, according to some requirements of this application. In this following example, we make the assertion that before we can assign any tasks to a new employee, a supervisor has already been assigned. You will want to make assertions about an object before performing a critical operation on it. This helps you to make your code more error resistant, and if something goes wrong in the program, you will have an easier time debugging it. This is a lot better than finding out through a side effect where the program fails somewhere else. The cause of the error is much easier to trace when you know that it failed because the program violated an assumption you made. In this example code, we used the assert option that returns a more useful message. Without it, we get no identifying information about the assertion other than the line number. On some versions of the compiler, you will need to use a command option to set the compiler's source compatibility mode when you compile your code. .4 or 1.5 depending on your compiler version. Now let's force an assertion to fail and see what happens. By default, the runtime environment does not enable assertions, and you must start the GRE using the EA enable assertions command option. This code would cause the following result. Remember that assertions are for true sanity checks, for conditions you believe should never happen. You should not use them in place of your normal error checking. Warning: do not allow assertions assertion statements to change state values in your code. When you eventually turn off assertions, your code will act differently than it did when you had assertions enabled. For example, do not do the following. You will want to leave assertions enabled throughout the development phase. Once you thoroughly test the system and move it into a production environment, you will probably want to disable assertions. There will be a slight performance gain in doing so. Don't change the code to do this, and don't remove the assertions. You want the assertions to remain in the code for documentation purposes anyway. That way, when changes are made at later date, the programmers will be reminded to keep all of the assumptions valid, and this will also be testable. Living on nanotime using system.nanotime. Moore's law is the name of a well-known observation that the number of transistors in a computer and its processing speed increase exponentially over time. Gordon Moore, as Director of Research and Development at Fairchild Semiconductor, made the observation way back in 1965. So far, it still holds true. With much faster computers now than we had when Java first arrived, millisecond timing is no longer good enough for many applications. Perhaps you have to use the java.lang.system class to obtain timing information for a method call or a section of a code using the current time millis method. We often use this to measure how long it takes to perform certain operations. However, the operation might take far less than a millisecond on faster computers, and we'd end up doing the operation hundreds or thousands of times in a for loop and dividing by the loop count to calculate the unit time. Consider the following. This was an easy calculation, since I used a for loop count of 1000. But what about sub-millisecond measures? If I were to project human feelings onto the code, that poor for loop would get awfully tired from the million count busy loop. Besides, the for loop method of timing is useful only in cases where there are no side effects from repeating the operation. If the operation were a call to the java.util.collections.sort method, it would be much more difficult to figure out how long the sorting process took. In Java 5, the system class has a new method, nanotime, that returns a nanosecond resolution counter. You can't use it for measuring absolute time, but it works great for measuring time differences. Unfortunately, we have no guarantee that we will actually get nanosecond measurements when we run this code. But with a faster machine, and a good GRE implementation, it's a useful measurement for testing purposes. You can find more information on this method in the GTK5 documentation. Because of operating system characteristics, machine processing speed, and system load, you may get a wide variation in the values returned by the nanotime method. This issue should improve over time. Moore's law almost guarantees it. Resources. For Moore's original paper, see Gordon E. Moore, Cramming Moore, More Components and Two Integrated Circuits. This article is also available online. See this book's website at http://wikidcooljava.com. Taking a very short nap, sub-millisecond sleep for treats. As we discussed in the previous section, Java 5 added a nanotime method to the system class to ensure that time measurements can keep up with faster systems. Even in earlier versions of Java, treats can have sleep times of less than a millisecond. You might recall that Java's threading mechanism has a sleep method that takes an int parameter representing the sleep time in milliseconds. There is also a sleep method that accepts the millisecond parameter plus an additional time in nanoseconds. If you set millisecond time to 0, then the thread will sleep for the specified number of nanoseconds. The same thing applies here as in the nanotime method described earlier. Because of operating system characteristics, machine processing speed, and system load, the actual sleep period could be different than you would expect. You shall remain nameless, creating an anonymous class. When you are doing Java development, you sometimes need to implement an interface that only has one or two methods, with only one or two lines of code for each method. This happens quite often in AWT and Swing development, when a display component needs an event callback method, such as buttons action listener. If you use normal classes for this, you'll end up with many small classes that are used in only single location. Many developers may not be aware that Java allows you to define inner classes, or that inner classes don't have to be used within a GUI framework. An inner class is a class that is defined within another class. You can define inner classes as members of a class, as in the following example. This is a simple implementation of a linked list in Java. The linked node class is an inner class of our linker class. Although it is contained within the linker class, it can still be accessed from other classes because we defined it as public. From other classes, you can create an instance of it by using new linker.linked node. One such class from the core API is the map.entry class, used by the java.util.map class. When you retrieve the set of key value entries in a map. You can also define an inner class that is local to a method. This type of class is visible only within the method where it is defined. You may want to do this if you are implementing an interface and you want to use the local class more often than once within the method, as this tongue-in-cheek example shows. We gave this local inner class. I like to think of it as an inner class, the name happy. This class cannot be accessed from any other class or methods. We used a local class only because we wanted to implement the smiler interface, which was defined within the happiness class. For many situations, it's not even necessary to give a local inner class name. It can remain anonymous. Anonymous classes are very useful for implementing interfaces that have only one or two methods, especially if we need to create an instance that is used only once.